Within the next decade, hedge fund performance may no longer depend on intuition or even classical computation. Financial optimization is fundamentally a mathematical problem, and mathematics evolves. While classical systems evaluate possibilities sequentially, quantum algorithms encode entire probability landscapes simultaneously. If scalable quantum hardware emerges, portfolio optimization will not simply improve, it will transform. Consider a portfolio with 50 assets. The number of possible allocation combinations grows exponentially. Classical optimization methods rely on gradient descent, convex relaxations, or Monte Carlo simulations. But as dimensionality increases, search spaces become rugged, nonlinear, and computationally expensive. This is not a failure of intelligence. It is a limitation of sequential computation. So what does this actually mean for a hedge fund? It means most portfolio optimizations are approximations. When markets are calm, approximations are fine. But during volatility, small optimization errors compound into real losses. The firm that evaluates better allocations under stress captures mispricing faster. In quantum computation, a system can exist in a superposition of states. Instead of evaluating one portfolio allocation at a time, a quantum register can encode exponentially many configurations simultaneously. Mathematically, the quantum state can be written as psi equals the sum over x of alpha x times ket x. Each basis state ket x can represent a possible allocation. In finance terms, this means the system is not testing allocations one at a time. It is encoding an entire strategy landscape simultaneously. If interference amplifies the most profitable structures, the algorithm isn't just faster. It is structurally advantaged in complex markets. Quantum algorithms do not simply try every possibility faster. They reshape probability distributions. Through interference, suboptimal solutions can cancel out, while optimal configurations are amplified. This is fundamentally different from brute force search. In markets, noise dominates signal. Most strategies fail not because they are wrong, but because they are drowned in statistical randomness. If interference can suppress weak probability paths and amplify strong ones, optimization becomes cleaner. Cleaner optimization means better capital efficiency. In classical Monte Carlo simulations, estimation error decreases proportionally to 1 over epsilon squared. Quantum amplitude estimation reduces this to 1 over epsilon. That is a quadratic speedup. For large-scale risk modeling, this difference becomes economically significant. Risk models drive position sizing. Position sizing drives survival. If a firm can estimate tail risk faster and more accurately, it can adjust exposure before others even finish computing. In competitive markets, speed of risk estimation is not academic. It is economic. But here's the reality. Current quantum hardware is noisy. Error correction is expensive, and practical advantage at scale has not yet materialized. The transformation is not happening tomorrow, but when fault-tolerant systems scale, optimization-heavy industries will shift first. Finance is at the top of that list. The real opportunity is not trading quantum hype. It is understanding where computational advantage migrates. When optimization changes, industries that depend on optimization reprice. Portfolio construction, derivatives pricing, risk modeling, all of these become computational races. You don't need a quantum computer to benefit. You need to understand which industries depend on optimization bottlenecks, because when the bottleneck disappears, the value chain rearranges, and markets always reprice rearrangements. If you enjoyed this journey into quantum ideas, like and subscribe to Stochastic Intelligence, where deep science becomes simple.